Good morning, Amherst. Got a long lesson for you today. A lot of notes. You're going to need your worksheet packets. You want your notebooks. You want your supplemental tables. As you can tell from the page in front of me, lots of vocabulary today. We're going to talk about operational definitions, conceptual definitions, Arrhenius acids and bases, Bronsted-Lowry acids and bases, conjugate acid-base pairs, the terms corrosive and caustic, hydrogen, hydronium, and hydroxide, amphoteric, and amphiprotic. That's a fistful of words right there. Today's lesson is brought to you by Quaker Boy Game Calls. This is a diaphragm call, a mouth call. This would be a good yelping hen call. That would be like an assembly call from a hen. And, well, just to compare and contrast it, here's a similar call, another diaphragm call, but this one is much more raspy. This is like an old cackling hen. You never know what they're going to want to hear. I don't claim to be a good caller, but I'm learning to speak the language. All right, got your stuff ready to go? So, operational definitions versus conceptual definitions. Okay, what's an operational definition? It's basically you define something by what it does. It's a screwdriver, it's a hair dryer. It's based on observable properties. You can see what it does. It's one of those things that does that. Give me the whatchamacallit. It's a hair dryer, for example. Well, whatchamacallit. What's the whatchamacallit? It's the thing that does that. You know, it's the little piece of gear that I put in the hole over there and I put it, whatever. It's, you know, you define it by what it does. Whereas a conceptual definition is something that attempts to explain what something does. Why does it do that? I don't know, but you know, it seems like when it does that, it's got to be based on this, and you go a little bit further. Okay, so let's start off with operational definitions of acids and bases. This is something where I really wish you would have had the lab because it's a whole lot of fun, because you actually get to see it and do it. But you're gonna have to take my word for it this year, okay? Please slide this up a little bit. Okay, so for acids and bases, we're going to have two columns here and a pretty good amount of notes. Both acids and bases conduct electricity when they're in solution. They are both electrolytes. That's a very interesting point there. Acids, bases, and salts are electrolytes. Now, bases start off being ionic. They dissociate in water. Acids start out being covalent. They ionize in water. Salts are already ionic. They dissociate in water. But molecules, true molecules, they don't conduct. Things like alcohols, they are non-electrolytes. Acids and bases are both electrolytes. Acids react with some metals to release hydrogen gas. We've seen this. We put our pennies in hydrochloric acid. We had etched them. The zinc on the inside reacted with the acid. The copper did not. As a matter of fact, there are many metals that will react with acids, and our next unit will get into that a lot more. But if you look briefly at table J and you find hydrogen down toward the bottom, you'll note that copper, silver, and gold will not react with acids, but anything above hydrogen will. So you might want to get table J here, just make a little line here. These things do not react with acid, these three right here. All of these will. Bases, on the other hand, they don't react with metals. Kind of boring in that regard. Acids and bases both make indicators change color. Now, there are a few indicators that you should just know. There are only 6 on table M, but you should know about litmus and you should know about phenolphthalein. The quote-unquote litmus test. Acids turn things red, bases turn things blue, litmus being red or blue. In the middle, it's kind of a purpley color. Phenolphthalein, acids make it colorless and bases make it pink. You should just know those. But red tends to be associated with acid and blue tends to be associated with base. Okay. So phenolphthalein is colorless in an acid and phenolphthalein is pink in a base. Litmus is red in an acid. Litmus is blue in a base. Table M has many indicators, but you'll see red as a recurring theme for acids most of the time. Acids neutralize bases, bases neutralize acids. They both undergo neutralization reactions. Acid plus base will give you salt plus water. Acids have a pH less than 7. Bases have a pH greater than 7. We'll define what that means later in the unit. But basically, 0 to 6.9, you're in the acidic range. 7.1 to 14, you're in the basic range. Another word for basic is alkaline. Acids tend to taste bitter, things like lemon juice, that's citric acid. And bases tend to taste bitter, things like dark chocolate, that would be basic. Acids don't feel slippery. They just, if you have a solution of acid, it just feels like water. Whereas bases are actually making soap out of you. They feel slippery like soap. Yes, through a process called saponification. They react with the lipids in your hands, and they start making soap out of you. Acids are described as being corrosive, meaning they'll react with you and metals and whatnot. Bases they're reactive, but they're not described as corrosive as much as they are caustic. There's the MSDS international symbol for corrosive, which actually looks like a piece of metal, and they have a test tube and pour it on there, and it's like corroding away, and they put your hand under there, and hey, they would just have your hand over here for bases. Little alliteration here: base, bitter, boring, blue. Words to live by. Remember we said lower left or larger, luster, loser when we talked about atomic structure? Well, base, bitter, boring, blue. Bases taste bitter. They don't react with metals. That's why I call them boring. And they tend to turn indicators blue. All right, let's move on to conceptual definitions. First conceptual definition was done by a guy named Svante Arrhenius. Some people call him Arrhenius, but I think it's Arrhenius. I think this is just a wild and crazy guy, Svante Arrhenius. Great name. So he's the first person to come up with, well, why does an acid do these different things? Basically, what makes an acid an acid? He says it's got something to do with the hydrogen. We've been using Arrhenius' definition on all of the worksheets we've done on acids and bases nomenclature so far. So he said, an acid is a substance that produces hydrogen ions, H-positive ions, as the only positive ion in aqueous solution. Okay, so he's limited to aqueous solutions, but he's saying an acid is an acid because of the hydrogen. So he says if I take an acid, HX, whatever X is, and dissolve it into water, it's the H-positive that makes the acid the acid. That's what's turning the indicators different colors. That's what's being generated. You get two of these and they're on two electrons. You have hydrogen gas coming out of there. All of the things that we see with acids, that's why. He said, well, a base is the substance that produces hydroxide ions, OH-, as the only negative ions in aqueous solution. Once again, he's limited to aqueous solution, but he's talking a base is a base because of the hydroxide. So if I took YOH, dissolved in water, you'd get Y positive and OH minus, and it's the OH minus that makes a base a base. It's kind of what we've been using for our nomenclature the whole time. Well, a couple scientists, Scandinavian guy by the name of Bronsted with the umlauts there, and a British scientist by the name of Lowry, they got together and said, well, what if I didn't have water in the system? Does it mean I can't have an acid or a base? They came up with a different conceptual definition of acids and bases. Now, in the Regents curriculum, they would call this an alternate theory. They kind of left their names out, but that's okay. They said bases exist in something called conjugate pairs. You can't have an acid without a base. You can't have a base without an acid. And the only difference between the acid and the base is one proton. Well, a proton is a hydrogen ion, right? If hydrogen is a proton and electron, take away the electron, you've got a hydrogen ion. So it's not too far off. It's something to do with hydrogen. They don't say anything about hydroxide, though. They said a Bronsted-Lowry acid is described as a proton donor, something that's going to give away an H positive. And the base is whoever takes it. It's a proton acceptor. So in Arrhenius theory, if I had hydrochloric acid, I'd say, oh, I dissolved it into water, produced hydrogen ions and chloride ions, and we'd call it a day. In Bronsted-Lowry, they said, no. Water isn't just the medium. Water is actually one of the players in the game here. If I take HCl, it interacts with water. The hydrogen transfers from the HCl onto the H2O, forming H3O positive and Cl minus. The H2O differs from the H3O positive only by that one proton. The HCl differs from the Cl minus by that same proton. The HCl has one more proton than the Cl minus. This is described as an acid, and this is its conjugate base. H2O differs from H3O positive by that one proton. This is the base. In order for H2O to turn into H3O, it has to accept that proton. This is the base. Here's its conjugate acid. So HCl and Cl minus are a conjugate pair. H2O and H3O minus are another conjugate pair. If I look at this for a second, things to note about conjugate pairs. Right off the bat, an acid-base conjugate pair is always on opposite sides of the equation. The acid has one more proton than the base. HCl looks a lot like Cl minus. That has more hydrogens than this. This is the acid. Here's its conjugate base. H2O looks a lot like H3O positive, but this has more hydrogens than that. One more hydrogen. This is the acid. Here's its conjugate base. Notice it's always an acid and a base, an acid and a base. The order doesn't matter, but you're never going to have two acids on one side and two bases on the other. It doesn't work that way. Now, H3O positive is the hydronium ion. We've seen this before. If I take a proton, just a proton, a hydrogen ion, and comes across water with a couple lone pairs sitting there, it says, I don't have any electrons, you've got a couple pairs you're not doing anything with. How's it about we form a coordinate covalent bond there, and I form H3O positive. Okay, so in this unit, the terms hydrogen ion and hydronium ion are interchangeable. They are synonymous. If I talk about hydrogen, I could be talking about H3O positive. Here I'm in Arrhenius theory. Here I'm in Bronsted-Lowry theory. But it doesn't really matter. For all intents and purposes, they are equivalent. When you get to college, you can talk about other conceptual definitions. They talk about Lewis acids, bases, electron pairs. We're not going to deal with that. So for our purposes, we've got operational definitions. We've got Arrhenius conceptual definition and Bronsted-Lowry conceptual definition. And when I'm talking conceptual, those two are basically the same. Now, sometimes vocabulary gets kind of funky and people start confusing hydronium with hydroxide. They are not the same thing. They are actually complete opposites. Hydronium refers to the acid part of a solution. Hydroxide refers to the base or basic part of a solution. So H3O positive is hydronium. It is not the same thing as hydroxide OH minus. Okay, in a Bronsted-Lowry pair, they're always on opposite sides of the equation. The acid is one more proton than its conjugate base. Let's look at worksheet 4, part 2, number 1. Let me grab my worksheet packet. So if you go to worksheet 4, there's going to be some definition stuff for you here. I'm looking at number 1 here from part 2. So here I have HCHO2 plus H2O, double arrow, CHO2 negative and H3O positive. If I look at it, I go, well, this one looks a lot like this one. That's going to be a pair. And this one looks a lot like this one. That's my other pair. And if you want to tell who's the acid and who's the base, you go, well, CHO2, CHO2 minus. That's got more hydrogens. This is the acid. Here's its conjugate base. H2O, H3O positive. This is the acid. This is its conjugate base. Easy peasy. Pretty straightforward. So the other 3 of those, and on the back page, well, I guess the other 7 of those are part of your homework. All right. Now, I like when they use this term species. Some species can be either an acid or a base depending on who they're with. You ever run into these people? You know, one day they act like, you know, they're your best friend. The next day they don't know you. Beware of these people. They grow up to be politicians. Okay? In chemistry, substances that can either be acids or bases depending on their partners, they're described as amphoteric or amphiprotic. Those mean the same thing, kind of like ambidextrous. If you can do things equally well with your right hand and your left hand, you're ambidextrous. If you can act like a conjugate acid or a conjugate base, you're amphiprotic or you're amphoteric. Okay, just a little vocab for you there. So here's an example. Here's HSO3 minus reacting with H3O positive to form water and H2SO3. This one looks a lot like that one. This one looks like that one. 3 protons, 2 protons. That's the acid. Here's its conjugate base. 1 H, 2 H's, there's the acid, here's its conjugate base. But consider the next reaction. Here's the same HSO3 negative, but now it's reacting with OH minus, forming H2O and SO3 negative 2. This one looks a lot like that one, but now it's an acid, and here's the conjugate base. This one and that one look kind of similar, but here it's an acid, and here's a conjugate base. Look at this. Top reaction, HSO3- is a base. Bottom reaction, HSO3- is an acid. Top reaction, H2O is a base. Bottom reaction, H2O is an acid. So both of these species could be described as amphoteric or amphiprotic. They behave differently depending on what other species they're interacting with. All right. In fact, water is notoriously amphoteric. Water can react with water. Sounds crazy, but water can display its amphoteric or amphiprotic properties when it reacts with itself. Water plus water, I can transfer one of these protons to the other water. It doesn't matter which way you go. I'm going to end up with H3O positive and OH minus. One of the molecules of water donates a proton to the other. Which one is up to you? You can do it, this way, or you can do it this way. In either case, here's water acting as an acid, here's water acting as a base. Here's water as a base, here's water as an acid. Water is amphoteric. One of the things you're going to find out is that polyprotic acids, acids with more than one proton, so the subscript on H isn't 1, they have amphoteric or amphiprotic intermediate species. That sounds pretty fancy schmancy. What's that mean? Here's H2SO4. That's a polyprotic acid. It's got 2 protons up front here, okay? 2 hydrogens. So if I removed one of them, I could be HSO4-, but I have another one to give. I could be SO4 -2. This intermediate species here, somewhere in the middle, I could gain that proton back and act like a base, or I can donate the other one and act like an acid. It's amphoteric. Here's phosphoric acid, H3PO4. I could donate 1 proton, donate 2 protons, donate 3 protons. This one could go back this way or continue on that way. This one can go back this way or continue on that way. These 2 intermediate middle species would be considered amphiprotic or amphoteric. Here's a clue. If you go to supplemental table 5, it's pretty easy to spot amphoteric species. Supplemental table 5. Now, they haven't quite done Bronsted-Lowry here. They're just showing the donation process. And I kind of wish they had gone a little further with this, but that's fine. HI, they used an equal sign instead of double arrow. H positive and I-. It's fine. They have an acid column here. They have the proton column. And then they have its conjugate base column here. So if you find on here HS-. All right, well, let's go to the acid column, slide on down, bam, HS- is right there. Go to the base column, slide on down, HS- is right there. Here and here. If you find a species on both sides of this table, both the acid column and the base column, it's pretty easy to recognize it, that species is amphoteric. Now, the other thing that's on this table is Ka. We're going to get into that. It's a big part of future lessons. But basically, Ka is KEQ for acids. It's a measure of products over reactants, a measure of how much the acid breaks apart. So the take-home message for today's lesson is that a bigger Ka means you've got a stronger acid. It's going to create more ions in solution. It's going to break apart more. It's going to just have more products and reactants, or at least more compared to another one. A bigger Ka means it's a stronger acid. So the higher up it is on the table, the stronger the acid it is, because they are arranged in order of, hey, that's really big, to, hey, that's really small. They get smaller as you move down. So let's go to worksheet 4, let's go to part 3, and look at number 1. Here they're making me predict which is going to be the acid, which is going to be the base, and which is the stronger acid, and yada, yada, yada. So I look at this problem here and I go, all right, so I've got PO4 -3 and HNO2. Well, right off the bat, this would appear to have no hydrogens to donate. This is not going to be an acid. So I'm going to label this one base right off the bat, and I can't have 2 bases on the same side of the equation, so this one's going to be an acid. Now, they are not conjugates of each other because they're on the same side of the equation. But if this species is an acid and it donates a hydrogen. This H positive is going to go over here. And if I combine H positive and PO4 negative 3, I get HPO4 negative 2. And if I took H positive away from NO2, it becomes NO2 minus. Now this one looks a lot like this one. If that's the base, this is the corresponding acid. This one looks a lot like this one. If that's the acid, here's its corresponding base. You go, well, I've got two acids in the system. Which one is the stronger acid? You go, okay, HNO2, right there. Got it. Bingo. HNO2. Okay, keep your pencil there. And HPO4 negative 2. HPO4 negative 2 is way down here. Okay, so HNO2 is a lot higher than HPO4 negative 2. HNO2 is described as the stronger acid. HPO4 negative 2 is described as the weaker acid. Now, there is an analogy here. If you're a strong acid, you are highly motivated to donate that proton. After you give away that proton, you don't want it back. A strong acid will have a weak conjugate base. A weak conjugate acid will have a strong conjugate base. It's kind of like I had this shirt when I was in 5th grade. It was a green polyester, big wide lapel mural of a Monte Carlo shirt. Well, by the time I was in 8th grade, it was time to give that shirt away, and nobody wanted that hideous shirt. So that shirt stayed in my closet for a good 20 years, but then, lo and behold, disco became popular again. I was trying to give that shirt away for years. Nobody wanted it. I was pretty motivated to donate that shirt. I was a pretty strong acid. Well, disco got popular again. All of a sudden, somebody wanted that shirt. Here you go, man. You can have it. Do you think I want that shirt back? Hell no. I was trying to get rid of that shirt for 20 years. After I donate it, I don't want it back. It's all yours. So a strong acid has a weak conjugate base. A weak acid has a strong conjugate base. In these problems, you'll always see that the strong and the strong line up on the same side. The weak and the weak line up on the strong side. And the equilibrium will always favor the strong. So this equilibrium, this is the favored reaction. Strong moves forward. Let's do one more of those. Let's do number 5. If I look at number 5, it's a little bit harder because I have two species here that they both have protons. H2S and NH3 both have hydrogens they could donate. So which one's going to act like the acid? Well, NH3 is dead last down here at the bottom, and H2S is up higher. Of these two, H2S is liable to be the acid. So here's my acid, here's a base. What do acids do? They give away protons. I had H2S, now I'm going to turn into H1S minus, and that's going to be the conjugate base for this pair. And if that hydrogen ended up here, NH3 is going to turn into NH4 positive, and this is my other conjugate pair. And if that's a base, this is the acid. Now let's compare these two acids, H2S and NH4. Go to your table. Here's NH4. Slide up, there's H2S. H2S is stronger. This is the stronger acid. This is the weaker acid. Strong goes with strong, weak goes with weak. Once again, this one, strong wins. It favors the forward reaction. So your homework today is to make sure you don't get confused about all this crazy vocabulary, and you're going to complete in its entirety, please, worksheet 4. All right, so it goes today. Friday, turkey. Have a good one.